Thank you, Shubhashri. Hello, everyone. Thank you very much for the invitation. So today I'm going to talk about the quantum access security of the Winternitz One-time Signature scheme. So this is a joint work with Dr. Christian Mayens and Professor Maris Osol. So the main goal of this talk is to describe how we develop a tool for analyzing hash chains in the quantum random oracle model using the superposition oracle technique by Zhandry. And then the second main goal is to prove the security of the Winternitz one-time signature in the quantum random oracle model, where an adversary has both access to the signing oracle and the random oracle. Here we will be using the approach by Allagic et al. So before we get there, we first of all define what is a digital signature scheme is and what is the notion of security for digital signature scheme. So a digital signature scheme is simply an asymmetric cryptographic tool that is used to verify the authenticity and the integrity of a message. So let's imagine that Bob is the receiver and Alice wants to send a document to Bob. So suppose that Bob is a lawyer, is Alice's lawyer, and Alice wants to send her testament to Bob in a way that he will not be modified while being sent in. So she prepare a public key that she make it to be known to everyone, and then she prepare a secret key that she used to sign her testament and send both the testament and the signature to her lawyer, Bob. And then now let's imagine that there is an active adversary in the middle of the communication. So then we are not sure whether the signature and the testament has not been altered. So according to the security of digital, how the security of digital signature scheme are handled, we have many types of digital signature schemes. In this work, we are dealing with hash-based digital signature schemes, which are schemes based on, for which the security is based on the properties of the hash functions. So we have, as example of hash-based signature schemes, we have the land port signatures, the Winternitz signatures, and the Merkle signatures. So the land port and the Winternitz are both one-time signature scheme, meaning that the key is only used once. And Merkle signatures are multi-time signature scheme. So in this way, we will focus on the Winternitz signature. So let us now look at the security of digital signature schemes. So we start by the standard security notion, which is the existential unforgeability under a chosen message attack. So whereby an adversary with a public key choose choose some messages of his choice and then supply them to the signer, and then he sign it and send back the signature for that message. And he can do that for a plausible number of message and receive the signature. Let's say for Q queries, he can make Q queries to the challenger, to the signer, and get back the signature. So he used that signature, those information, to learn some information about the secret key and come out with his own message and signature pair. So such an experience is known as the chosen message attacks. And then we said that an adversary succeeds if the message query is different to all the queries one, and then the signature for that message is valid. So we said that a digital signature scheme is secure under an existential unforgeability chosen message attack if no adversary can succeed this game with non-negligible probability. So we can ask now a question that what if the adversary has access to a quantum adversary, and then now it will not just do a chosen message attack, but a quantum chosen attack whereby it chooses some messages, it will query messages in superposition and receive the signature in superposition and do some computation and measure them to get classical forgery. So in this case, the notion of EU-CMA is not well captured because we can't distinguish a classical message to quantum messages. So it's unclear whether there is quantum attack or not. So now looking at this limitation to some quantum notion of definition has been proposed, like the Bonnet and Zhandry security notion, who says that after making Q queries, if a digital signature scheme is secure if after making Q queries to no adversary can forge Q plus one different message signature pair. And then we have also the one-time unforgeability, whose the main goal is to translate quantum attacks to classical attacks. And this is only for one query. And then we have now the blind unforgeability notion of security. That's the one we are going to use to achieve our proof. So the idea of the blind unforgeability is that, okay, since the problem is to distinguish the fresh forgery, the adversary's message to the queries ones, in the blind forge experiment, we said, okay, if you have a message space, then we choose a subset of the message space for which all the messages belonging to this set will not receive the signature. So if an adversary queries a message that belongs to this subset, it will not get the signature. And its goal is to come out with valid signature for messages belonging to this set. So we will say that using under this definition, an adversary can succeed if the message it come out with is different to all the queries one, and then the message belongs to the blinding set and the signature is correct. So let us more formally define the blind unforgeability notion for digital signature schemes. So when we said blinding, what we mean is that if we are using a blind oracle, sign oracle, if the query to that oracle is M, the sign oracle first of all check whether the message belongs to the blinding set. If it's true, then it output a dummy symbol, just this, so it will not provide a signature. Otherwise, it provides a signature for that message. So the notion of security, of blind unforgeability security relies on the following game. The game known as the blind forge experiment, whereby the first step is that the challengers generate a secret key, a pair of secret and public key, giving a security parameter n. Then it select the blinding set by putting some messages in this subset B independently at random with probability epsilon. And this probability, this factor, is given by the adversary at the beginning of the challenge. So the next step now is the interaction of the adversary and the blind signing oracle to come out with the forgery message signature pair. So the final step of the blind forge experiment is to verify the forgery message. So the challenger will output 1 if the message is, sorry, will output 1 if the message belongs to the blinding set and the signature for that message is valid. Otherwise, it outputs 0. So we said that a digital signature scheme is blind unforgeable if for every adversary with a blinding sign oracle, the probability that the adversary wins the game is negligible in n. So now that we know what a digital signature scheme is and how the security is managed for digital signature scheme, we move now to the description of the Winternitz One-time Signature scheme for which we intend to prove the security in the quantum random oracle model. So the Winternitz One-time Signature scheme use a hash function, a random hash function. In our case, that function has the pre-image resistance. So that hash function is used to generate the secret key and also to generate the signature. So in the Winternitz one-time signature scheme, there are some parameters, n, which is the security parameter that determine the length of the keys. We have the Winternitz parameter, which is used to trade off the signature size and the signing and verification time. We have the A, which is the message length, and the L, L1, L2, and L are computed from the previous parameters. So all those parameters are known. So now the key generation, how is the key generation made? The key generation is made by 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 giving a hash chain. So by constructing a hash chain, whereby the first element of each hash chain is generated uniformly at random, and we use it as the secret key. And to get and the type of the hash chain is the public key. To get to get the next element, we apply the hash function to the former element. So that's how the hash chain is get the our secret key are obtained. So now to sign the message is not signed bit after bit, but instead the messages is first encoded in blocks, L1 blocks, encode in the omega base representation. And then we compute the checksum. The checksum is like a security step. So we compute the checksum. And then we encode also the checksum in L2 blocks so that all the blocks form, we have L blocks. And those blocks are also encoded in omega base representation. So finally, our message is this block is the concatenation of the first blocks and the checksum, the block coming from the checksum, you have this. So, and the checksum has a nice property that the blocks of a message is unique in the sense where if you compute the blocks of one message, M, let's say M, if you take any other message, let's say M prime, and you compute the blocks of the message M prime, you will find at least one position where one of those blocks is smaller than one of the block message of the message, the original message. So now when the message is already in block, the signature is just made by applying the hash, evaluating the hash function bi time to the secret key, to each secret key, and then we get the signature as you can see here. And the verification, to verify, we evaluate the hash function in the remaining part. So let's say I will just go to this slide. Let's say maybe bi is this one, this element. So we evaluate the hash function so that from this part, we evaluate on this element. And if we get the public key, we get this element, it means that this signature is correct. So it's what is a bit explained here. So now that we know what the Winternitz signature, how it works, now we move to the quantum security of the Winternitz one-time signature scheme. So our goal is we want to show that for any adversary, having a public key is difficult for him to find the corresponding secret key. For that purpose, we show the following theorem. We show that the Winternitz one-time signature is blind and forgeable if the use hash function is modeled as a quantum accessible random oracle. So in other words, we want to show that the success probability of any blind unforgeability adversary against the Winternitz that makes Q quantum queries is bounded by this expression. So here CW is just a constant, Q is the number of queries, A is the message length, W is the security parameter, and N is W is the Winternitz parameter and N the security parameter. So in more formal, our approach to show this theorem is to execute the blind forge experiment and analyze the success probability of an adversary to win the blind forge experiment. So for that, we know that in the blind forge experiment, as we explained above, the secret key is only used by the blinding sign oracle. So what we can do, we can modify the experiment. So we can modify, while analyzing the blind forge experiment, we can modify the key generation, we can modify the random oracle, we can also modify the signing oracle, as long as they are indistinguishable from the real one in the view of an adversary. And we will call this modified experiment, we will refer to it as the quantum independent world. So now we explain how exactly we modify the key generation, the random and the signing oracle. So the way we modify the key generation as follow. So we prepare the secret key as a uniform superposition. So they are a uniform superposition, as well as all the intermediate hash, all the intermediate hash chain. And then the public key is generated uniformly at random. Then we reprogram the random oracle such that it is compatible with the hash chain. So this state new is just like the summary of all those written in the mathematical form. So now we describe how the our blinding signing oracle works, as well as our random oracle. So if we imagine that X is the query, is the adversary query to the random oracle, the random oracle compare X to the hash chain. So if X is equal to one of the hash chain elements, let's say gamma ij, then the random oracle answers the query with the next hash chain element, gamma ij plus 1. And if X is equal to multiple hash chain elements, the random oracle answers the query with the, the following hash chain elements of all of them, all those multiple hash chain. And if instead the query X is different to the whole hash chain, then the random oracle apply a random hash function to the input adversary. So that's how the random oracle works. Now, the blinding sign oracle compare why it receive, why is query. It first compare if the message, the query is blind or not. If the message is blinded, then it doesn't provide a signature, but rather a dummy symbol, the bird symbol, as you can see. But now, if the message is not blinding, then he answered the query with the signature, and the signature is composed of all the hash chains all the hash chain elements corresponding to the blocks of the message, of the messages as we have seen above. So now we were able to show that our quantum random independent world is indistinguishable to the real world. In fact, more formally, we show that if we have P and Q, which are the outcome distribution to an algorithm that interact with the real world and with the quantum independent world, then the two distributions are close up to the factor of 3, this expression. And since W and L are constant and N is quite large, since it's the security parameter, this factor happens to be negligible. So now that we know how our quantum world works, let us now see the general approach, the general interaction with that the adversary proceed to come out with the forgery. So in our analysis, we allow the quantum adversary to query the random oracle. So he has the possibility to query the random oracle and get some information, because his goal is to learn as much as information as possible about the hash chain element to be able to come out with a correct signature. So he can query the random oracle, learn some information, query now the sign oracle at most once, get the signature, learn some information, and also query the random oracle again, a polynomial number of time, anytime number of time he wants, and then get the information and use all those information to learn something about the hash chain and get the classical forgery message and signature. So now the next step of the blind will be to verify if the message is valid or not. So by let's start with the where we approach. We only allow the quantum adversary to query the signing oracle. So let us first look where the case where the quantum adversary only has access to the blind sign oracle. So in this case, we have seen he prepare a superposition of messages and supply them to the blind sign oracle and get back the signature, as you can see here. So um, mathematically, he prepare a state in superposition, supply it to the sign, blind sign oracle, get the signature, and makes some computation to learn some information about the hash chain. And those computations can be viewed as applying some unitary to, to the state. And then you get this state. You then measure the M register to get the message, the classical message, forged message, and also measure the sigma register, the signature register to get the signature, the first signature for that message. And then this is the post adversary state. So now to verify, we first of all check if the message belongs to the blinding set. If it's not the case, then the adversary lost the game because the first message has to be in the blinding set. So if the message belongs to the blinding set, then we go on and verify the signature if the signature is valid. So to verify the signature, we first know that the hash chain, as we explained above, the hash chain works only in the forward direction. So the classical notion of security for the Winternitz is that the path below the query position is unknown to the adversary. So, and we also know by construction of the checksum that if this message M has been queried to the sign oracle, since this message M belongs to the blinding set is different from this. So by the construction of the checksum, we know that there exists a position where one of the block of the message, this message is smaller than the block of the signing message, the query message. So we know that for that particular position, the hash chain elements relevant is still in uniform superposition. It has not been used to sign this message. So since it's in uniform superposition, it means that this signature, the first signature, is independent of that hash chain elements. So that's our intuition. But now this, we can easily check it in classical setting whereby we only query one message and we can find that position easily. But in quantum setting is not the case because since this message is a superposition, a linear combination of different messages, then this position is different from each term in the superposition of messages. So now to find this position, we perform an outcome measurement, L plus one outcome measurement, a partial measurement only on the hash chain register, only in the hash chain to find that position. And this idea of partial measurement is due to Allagic et al. So if our partial measurement give outcome I in I from 1 to L, as we have seen here, our signature contains L, L string, L n-bit string. So if the outcome give one of those, then there exists at least one hash chain element that is relevant for the forged message that is in uniform superposition state. And that it means that the forged signature is independent of that hash chain element. So, and then we have also shown that the case where L plus one, the outcome L plus one, where none of them is in uniform superposition can never occur. So we have shown this. So it means that we have successfully shown that gamma, the first signature sigma star is independent of at least one of the hash chain elements relevant for that signature. So given that this one of them is in uniform superposition, one of the hash chain element relevant for checking the signature is in uniform superposition, it means that it's uniformly random. So the probability to get the right hash chain element is 1 over 2 to the n. So from that, we compute the success probability of providing all possible message and signature per forged message and signature paired, we compute it, and we get we found that is less than equal to the L plus 1 over 2 to the n. Okay, this L plus 1 comes from the partial measurement. Remember that in our original blind forge experiment, there is no partial measurement. So by the pinching lemma, this partial, if we want to compute the probability in the real world, this partial measurement can only increase the success probability of the adversary by at most L plus 1. So that's why we get the probability at most L plus 1 over 2 to the n. But now, due to the fact that our independent world is close to the real world up to a factor, up to this factor, we have to add that factor to the final success probability, and we get this probability. And we can see that since W, the security parameter, and L, the number of hash chain, since they are both constant, this probability depend on the number, the security parameter n. And since the security parameter is quite large, this bound happens to be negligible. So now let us look at the case where hash queries, in addition to query the signing oracle, an adversary can also query the random oracle. So our goal in this case is to show that hash queries do not disturb too much the superposition hash chain. So we first consider the case where the adversary can query the random oracle before querying the blinding signing oracle. So the adversary can prepare some state in uniform superposition, supply them to the random oracle, and the random oracle answers the query. It can do that for a plausible number of times, let's say Q0. So here, this is our adversary state after making Q0 hash queries. So the adversary start with this new is the hash chain that is in uniform superposition as we defined above. It starts with an initial state psi, and then the random unitary, oracle unitary is applied. Then V1 can be viewed as internal computation for the adversary. Then it query again and the random unitary is applied. And then it makes some internal computation again. So it can do that Q0 time and then get this state. This is the state after all the hash queries. So now we want to show that those queries do not disturb the superposition hash chain. But we know that at the beginning, before any queries, all the hash chains are in uniform superposition except for the last one, which is the public key. So we can project the superposition, the hash chain being in uniform superposition, we can project it to this state and compute the difference to see if they are close or not. So when we compute this Euclidean distance, we get this bound, this number. And again, since W and L are constant, this number depends on the number of queries and the security parameter. So to compute the magnitude of, so for this bound to be negligible, the number of queries has to be at smaller than 2 to the n over 2. That's why we said this bound is negligible unless the number of queries is at least 2 to the n over 2. So it means that those two states are close. So meaning that the hash queries before the sign query does not give too much information, a significant information about the hash chain to the adversary. So it can help him to get the correct significant information and being able to provide a good signature, a valid signature. So we can also do that. We can perform similar procedure, similar analysis for the case of hash queries after sign query. And we when we do those computation, we come out with this bound, this Euclidean distance that is equal to this number. And this expression, we can also see that in the case of hash queries, we suppose that the adversary makes Q1 queries. So we can also see that since this of W and L are constant, are constant, and this number again only depend on the number of queries and on the security parameter. So, and this number again can be negligible if the number of the number of queries is not is smaller than this factor 2 to the n over 2, 2 to the n over 2. So, which means again that even hash queries after sign queries do not give enough information about the hash chain to the adversary. So he has negligible probability to provide good, to make use of the hash chain and being able to come out with a valid signature. So if we combine all those bound, those results that we have seen previously, the bound for hash chain before the sign query, the probability, the success probability of the adversary, just in the case where the adversary only query the blind sign oracle, and also the bound for hash queries after signing, after making at most one sign query, together with the bound coming from the difference between the quantum independent word and the real word, we come out with this expression. And this probably, and after making some computation, we get this, where Q is the maximum number of hash queries, the queries to the random oracle. So it's given by Q0 plus Q1. And this L, since this L depend on the message length and the omega and W, the Winternitz parameter, as we have seen in the description of the Winternitz, we can rewrite this L as follow. And again, looking at these parameters, we see that again W is constant, and also those numbers are constant since W is constant and the message length is constant. So it depends again on the maximum number of queries and the security parameters. And making similar analysis and in the case with hash chain, with hash queries, we found that this parameter is again negligible under certain number of queries to the random oracle. So, and from this result, we can say that the Winternitz one-time signature scheme is secure, is blind, unforgeable, one-time blind, unforgeable. So, as a takeaway, in this work, the goal was to show that the Winternitz one-time signature schemes is blind unforgeable, is secure in the quantum random oracle model. So we first of all develop to achieve our proof, we first of all develop a superposition hash chain that we use as keys for our analysis. And then we show that in the case where an adversary is only given access to the blind signing oracle, the first signature sigma is independent of the hash chain. So the adversary can learn much information to provide a valid forged signature. So in that case, the success probabilities of any adversary is negligible. And we also show that even when the adversary has access to the random oracle, the hash chain superposition is not disturbed too much. So the adversary learns insignificant information about the hash chain, and thus the success probability of an adversary of winning the blind forge experiment is negligible. And this one is a sort of comparison. It's not in the talk, but it's a sort of comparison of our bound with a Grover search algorithm for finding the secret key corresponding to the public key. So we found that our bound that we get give a beta bound. Our scheme, our analysis give a beta bound if we want to extract the number of query in this one, and then we compare to the number of queries we have to make to a Grover search algorithm. We were able to find that our our approach gives a better bound in terms of the number of queries. So to achieve this, we use the superposition oracle techniques, the reprogramming of the oracle, and then we use the measurement to extract the position where at least one hashing element relevant for the first signature is in uniform superposition state. And then we use the hashing element. So as future works, we intend to look at the multi-time signature, such as the Merkel signature, and also it will be good to implement those security to really see how good is the bound. Thank you.